Hello, calculus fans. Let's take a solid spherical ball. So this is not just a sphere, it's a solid sphere. And let's find the mass of this thing. And we're going to suppose that the mass density at any particular point is proportional to its distance from the z-axis. So our mass density function is k times square root of x squared plus y squared. K is, of course, the proportionality constant, and square root of x squared plus y squared measures the distance from a point to the z-axis. Let's convert this mass density function into spherical coordinates. We'll need to do that when we convert an integral for the mass into spherical coordinates anyway. So our mass density function looks like this in spherical coordinates. K times the square root of rho sine phi cosine theta squared plus rho sine phi sine theta squared. We square those terms on the inside, and now we can try to factor out some things. And when we do that, we get a very nice expression that we end up with a cosine squared theta plus sine squared theta, which can be turned into 1, which makes the whole expression much simpler. We end up with k times rho squared sine squared phi, and we can square root these things now because both rho and sine phi are positive. So we actually end up with a very nice expression for our mass density function. It's going to be k rho sine phi. And then, of course, we can describe the ball in spherical coordinates as the set of all points rho theta phi, where rho goes between 0 and a, theta goes between 0 and 2 pi, phi goes between 0 and pi. All right, last thing to do is to write down and evaluate an integral for the mass of the ball. The mass is going to be the triple integral over b of the mass density function. And when we write this in spherical coordinates, we get this. The integral from 0 to pi, so that's phi. Integral from 0 to 2 pi, that's theta. Integral from 0 to a, that's rho. And then we have two things that go in here. First, there's the mass density function, k rho sine phi. And then we have our scale change factor that just has to go in any time we're converting from rectangular to spherical coordinates. Everything in here factors because all the limits of integration are constants, and we're actually able to factor the integrand. And if you'll recall, this particular integral, we have a special way of evaluating it. That integral actually works out to be pi over 2. And so when we combine everything all together, we're going to end up with k times pi squared times a to the fourth all over 4. Remember that k is our proportionality constant. A is the radius of the sphere. Okay, that's all for now.